Welcome everyone. My name is Elia. I'm a junior scientist at the Advanced Scientific Computing division of the CMCC Foundation, located in Regression, and I'm also a PhD student at the University of Salento, located in Regression. Today with me, there's my colleague Fabrizio Antonio, also from the Advanced Scientific Computing division from CMCC, which will be giving a demo later on in this session. Our activities are mainly in the field of computer science, and in particular in data analysis. Online, there's also Nicholas, which will be giving the presentation on the next session next Tuesday. So this course is being organized by CMCC and our colleagues from DCARZ as part of the activities of the ESiWACE2 project, which is the Center of Excellence in Simulation of Weather and Climate in Europe. One of the goals of the project is to provide some specialized training to transfer knowledge and enhance HPC capacity in the weather and climate domain community. The training course aims to provide an introduction to high-performance data analytics and visualization applied in the context of weather and climate. There will be lots of space for practical examples with tools such as Ofidia and ParaView, and there will also be some hands-on where you can actually play with these tools and test some of these examples yourself. So as you saw, when registering, the course is organized in 4 2 hours lessons, which are distributed over the full width of October. Basically, we will have one lesson per week. Today is the lesson will be presented by me and Fabrizio from CMCC. We will provide an introduction to high-performance data analytics into the Ofidia framework, and then show some demo and some examples into the Ofidia module. Next week, there will be a session focusing more on the visualization aspects, which will be managed by Niklas and Florian from DCARZ. And then there will be other 2 sessions following in the next 2 weeks, which will cover more advanced concepts from Ofidia and ParaView. Here, I just put some quick info that are useful for the general organization of this session. So, as I mentioned in the email that we sent a couple of hours ago, please mute your mic and switch off your webcam during the presentation. Also, remember that this will be recorded and later published. So, if you don't want to be recorded, please leave your camera and microphone always off. If you have any question during the lecture, we can use this Google Doc. You have received the link on the email. We will try to address the questions at the end of each talk. Concerning the hands-on and the demo, we have prepared a virtual machine. So if you want to actively take part to this hands-on tutorial, you should have set up this virtual machine, and then you can get the notebooks from the GitHub and try to run them. So if you want to get more information about the ESiWACE2 project, you can visit the web page. I don't know if there are any questions before we start. Okay, so I think that we can start with the first talk of this session. Just switch the slides. Okay, so in this presentation we'll provide a basic introduction on high performance data analytics and in particular at the Ofidia framework. I just put a brief outline of the content which is going to be covered. So we first provide a very brief introduction of the main data challenges in science, and in particular in the field of climate change, and just give an introduction to high-performance data analytics, and then we'll go into the details of the Ofidia framework, which is a framework for high-performance data analytics, which is developed by CMCC. After this, then Fabrizio will give a demo showing an overview of the main features which are provided by the PI of Ofidia modules, and then we'll move in the last part of this 2-hour session on a hands-on in which you will be able to run some notebooks using the PI Ofidia features on the virtual machine. Before going to the introducing the Ofidia framework, just want to give an overview of some which are some important challenges for climate analysis. As you know, the continuous increase in the data set which we have been experiencing in the last 10-15 years poses several challenges that must be tackled by the system in order to efficiently manage, store, and analyze this data. As you may know, the term big data has in fact emerged from the beginning of the 21st century, representing all those data which were too big to be analyzed with traditional systems. And so these issues are also issues which are known in the context of scientific data and also in the context of climate and weather. In fact, for climate science, it is critical to have some infrastructure which is fast and reliable for getting large quantities of data. This because non-trivial climate analysis requires multiple input data, which can also be needed from different models. To date, this requires to download the data from the different sources to the local infrastructure. We think at gigabytes or terabytes of data. This step already represents a big barrier for scientists due to the time which is needed to download this data. But if we think 2 petabyte data set, then it's simply appears that it's not doable. So new approaches are needed to reduce data movement. One of these approaches, for example, by exploiting server-side technologies, which move the computation to the server side, and leaving on the client side just very simple tools that will download just the final result of the analysis. Besides this, climate analysis also could be composed of very complex experiments, including hundreds of analytics operations. And so the supporting of end-to-end workflow solution is another key point which has to be addressed in order to actually support analysis at a larger scale. This slide provides an overview of the increase of data in the context of the SNP coupled model intercomparison project. As we can see, these are the data science of the various phases of this project. The last completed one was the SNP 5 phase, which produced about 3.5 petabytes of data. Now the SNP 6 phase is currently ongoing. It is expected to produce up to 10 times more data, so something between 20 and 40 petabytes of data. Of course, analyzing and managing this big quantity of data requires solutions which are able to scale with the size. So design high-performance data analytic solution can actually support these big data volumes. So here just provide an introduction to what the meaning of high-performance data analytic. As I said, big data is a relatively new field which has been developed basically in the last 15, 20 years. The development of the big data ecosystem has also been very, very rapid. There's been an impressive effort in the development and evolution of software tools and systems. But this development have occurred in most cases outside the scientific computing field, whereas in the case of scientific computing, like for simulation and modeling, the experience has been built over decades using extensively parallel computing and high-performance computing hardware and architectures. So the developments in the two fields have been mainly disjointed, and this leads to a certain divergence into these ecosystems. And these are different from various points of view, like for example, in terms of storage architectures or of parallel computing models, also in terms of hardware and networking. However, in the last few years, the two communities are looking forward to provide a convergence of the technologies into the two fields, and this will allow the communities to benefit from the improvements of both these ecosystems. And this has led to what is called high performance data analytics. So the Ofidia framework is a high performance data analytics framework, which is developed by the CMCC Foundation and try to address some of the scientific data challenges which were mentioned in the previous slides. Some of the key aspects of the framework is that it provides a high-performance data analytics solution, joining both techniques and paradigms from data-intensive analysis and HPC. It implements a server-side approach, which moves the computation close to where the computing infrastructure resides, and it provides also an in-memory engine for parallel data processing. Besides this, it implements a multidimensional array-based storage model, which allows to partition and distribute data on hundreds of computing nodes, and it also provides end-to-end mechanism to support complex workflows by leveraging also the data cube abstraction. Before going into the details of the framework, I just want to provide an overview of which are the challenges which are addressed by the framework. So at the time when we started developing Ofidia, the typical workflow which was followed by the scientists was to basically locate the data on various data nodes, then download this data locally, set up the environment if some tools were required, and then run the analysis by using the local resources. With Ofidia, we provided a shift in this paradigm. So we moved the processing close to the data center, to the computing infrastructure, and this allowed the scientists just to install very, very lightweight clients which can interact with the server side components, and then just download the output of the results, which typically consist of few kilobytes or maybe a couple of megabytes. It's much smaller than the actual input data set. Besides this, some of the requirements which are mainly connected to end users applications that are targeted by Ofidia are the support for time series analysis, for data subsetting, also for model intercomparison or for multi-model intercomparison, or for sort of high thread computing data reduction and transformations. Here we can see one of the key aspects of the Ofidia framework, namely the shift of the computing towards the server side. Basically, what happens is by using client-side tools like the Ofidia terminal, which is a rich command line interface, which is very similar to a typical shell, or the Ofidia module, which is the Python interface to the Ofidia framework. We can start the analysis by sending a request to the Ofidia server, which is installed at the computing infrastructure or data center. And based on this request, the Ofidia server will then submit the execution of the analysis on these compute nodes, and then just give back an information about the computed result, which will be stored into a data cube. The Ofidia framework has been designed for multidimensional data analysis, so it is flexible enough to be applied to different types of scientific data, although it is mainly used for climate data. This slide will show just some of the projects in which Ofidia has been and is currently involved. It has been applied for very different use cases, for example, for fire prevention, or in the case of traffic analysis, but also for the analysis of climate data in very different projects, like in particular in the case of ESiWACE, Ofidia is being considered as one of the systems targeting large-scale applications. This slide shows an overview of the Ofidia architecture. It is a layered architecture composed of different modules. It has been designed to be very scalable, so that we can add additional nodes, and the system should automatically scale. Using a bottom-up approach, I will go through the various layers, starting from the lowest layer, which is the storage layer. Here we can see that there are two main parts: the Ofidia DB, which is the system catalog, which is used to map the whole data fragments which are related to a particular data cube, and then data can be distributed and on different storage devices, which are accessed by the I/O and analytics nodes. Here we can see a graphical representation of the storage model that we implemented for Ofidia. The idea was to provide a model which was able to scale with data size, and also able to distribute the data load on multiple nodes. So just to simplify, we can consider starting from an Sdf file, for example, with climate data, and then map this into this table, in which we have n+1 columns, where the first n are related to the various dimensions, like, for example, latitude, longitude, time, whereas the last one concerns the actual measure, like, for example, the temperature. Then we apply a two-step procedure, which makes the storage model basically independent from the number of dimensions. So in the first stage, we select one or more dimensions, and all the data which are related to these dimensions are grouped together into binary arrays. We refer to these dimensions as implicit dimensions, since they implicitly identify the data into the array based on their position. And then the remaining dimensions are merged together by means of a mathematical transformation, in order to compute a single key for the full set of dimension values configuration. And this leads to a table which basically has just two columns, this key identifier and the binary array. At this point, we can think as the data cube as a very big table. So Ofidia then partition this table into smaller fragments and distributes them on the various I/O and analytics nodes. This I/O servers here. So here we can see an example of an Sdf file with climate variables. And so here we have a temperature, latitude, longitude, and time. And we can see that how this is logically mapped to a data cube. So as we can see here, for each dimension, in this case, this is a three-dimensional variable measure. Here we have a cube for the whole variable temperature, and then based on the dimension values, we will have the values into the different cells. In this case, these are not actual values, but these are just indexes. This is just to give an easier way to see how the data is organized into this structure. This basically the data cube abstraction fits very well for many type of multidimensional data. So since basically the climate data is multidimensional, you should not surprise that it fits very naturally to this representation. Here I would like to show how the Sdf data is then mapped to the Ofidia storage model, just to clarify the previous slide. If we start from this Sdf file, we see that the time dimension is used as the implicit dimension. And then the remaining dimension, latitude and longitude, are used to identify the various binary arrays. Actually, this is not what we have in Ofidia. What we actually have is a single column with the identifier. And so we have an identifier which is associated to each binary array. From the point of view of data, it is worth mentioning that besides loading the data, the framework is also able to automatically adapt the data layout based on the specification of the dimension. So in this case, since we have specified the time is the implicit dimension, but since time is also the most external dimension of this variable, the data are actually stored into a different organization. So we have data which is stored contiguously with respect to time, and this will help us when we run the analysis stage, since it will provide better performance. And then this big table set is partitioned in multiple fragments, and what we have stored in the data store are actually a lot of these fragments. From the point of view of the user, what the user actually sees is not the single fragment, but the user sees the whole data cube as a single data structure. And Ofidia provides also several operations to handle this data cube, like for example, move them into different folders, also to create folders to better handle the virtual file system composed of multiple cubes. The second layer of the architecture consists of the I/O and analytics servers. The I/O and analytics servers are called in this way because they do not only perform the analysis, but they also handle import and export of this data from and to the data storage. So in these I/O servers can be deployed on multiple nodes, even hundreds of nodes, and they take care of loading the data from the Sdf file and then exporting it again back into Sdf files. We currently support two types of servers. We have MySQL-based server, and then a native server, which is the in-memory one, which provides better performances and allows to run the analysis by just fully in memory. To analyze this data, we have implemented the primitives, which are basically user-defined functions. We have implemented around 100 primitives, which perform different types of operations. Just to mention some, they provide features for running subsetting, predicate evaluation, statistical analysis, mathematical expression, and so on. These are applied at the level of the single binary array, and they can also be nested to build more complex functionalities. From the point of view of the users, this can be accessed with the OPH apply operator. And in the next slide, we see an example. Here we are running a nested primitive, which we are computing the box plot components on a subarray of this binary array. And here we can see that this is applying the whole binary array, and for each one we are computing these 5 values that are useful to create the box plot. This can also be run on multiple rows, as in the case of aggregation primitives. In this case, what we have is that the input data is composed of multiple time series, and then as output data we get a single time series with the average of the input data. Then at the level of the framework, we have the Ofidia framework, which provides an environment for the execution of the operator, which are parallel based, and they exploit a hybrid approach based on multiprocessing with MPI and multi-threading based on POSIX threads, and this allows to run very parallel operations. We have done some benchmarks and we're able to reach at least operation with around 6,000 threads. As for the operators, manage the whole data cube as a single structure, so it doesn't differently from the primitive which are applied on single binary arrays. The operator takes care of the whole data cube, so the whole fragments and the whole binary array stored into these fragments. We have implemented about 50 operators, which provide both features for data and metadata processing. The table shows some of the most used operators. This is an example of the export cube operator, which allows to export data. Here we can see the interface. Basically, after specifying the operator name, we can specify the list of arguments by using this key equal value format. Here we can see we can specify also some setting filters to just explore a block of the data in which we are interested. There are also support for different metadata operators, like for example the cube.io, which allows to see the provenance of a data cube. And so here we can see in this graph, which is produced by the Ofidia terminal, the list of operations which have been applied on the input data cubes. Then at the upper layer, there is the Ofidia server, which takes care of handling the requests from the client side and from the various type of clients like the OPH term or the Ofidia module, but it also supports clients through a WPS interface. Besides this, it also manages the execution of whole workflows and also the authentication and authorization of the different users. So thanks to this architecture, the Ofidia framework is actually able to provide 3 levels of parallelism. So the first one is at the level of the data cubes, which is based on the so-called massive operations. So these are operators which can run the same type of processing on multiple input data concurrently. Then the second level of parallelism is at the level of the framework, in which this is more high-performance computing paradigm, exploring MPI and POSIX threads, which we can run a single operator with more processes or more threads. And then the third level is at the level of the fragments, where we can exploit OpenMP to run concurrently on the binary arrays. One of the issues that is very common when using these frameworks on high-performance computing clusters is that it might be a little complicated to run these tools on the computing node. So to this end, we provide the features to deploy and undeploy the framework components on the cluster nodes on demand. So by using this very simple command, we can, for example, ask the scheduler 64 nodes, which will be used to deploy the I/O and analytics service. We have tested this with Sdf and LSF schedulers, so the system is actually able to interact with this scheduler to deploy the resources. We have done some tests on the Zeus supercomputer at CMCC. Thanks to the Ofidia server, each user is actually able to deploy multiple small clusters, and also different users can also deploy the cluster, and this allows to the different user to work on this partition of the cluster without any issue in terms of concurrency to the resources. So as mentioned, Ofidia provides also a Python interface. As you may know, Python is a very well-known programming language. Maybe it's the most used one for data science. It is very easy to learn and provides a very wide range of scientific modules. So for the Ofidia framework, we also provide these Python bindings, which allows to run all the Ofidia operators from Python scripts and also from Jupyter notebooks, and it allows also to integrate the Ofidia features with the features of other Python modules, like for example with Matplotlib and Cartopy for the creation of maps, as we would see in the demo, which will be provided after this presentation. In this slide, I just want to give an overview of what we can do with Ofidia. The meaning of the various cells is not very important now. We will see this more in detail into the demo. Basically, with this second line and the last line, we can deploy and undeploy the set of I/O and analytics servers, and then we can specify through the interface the number of fragments and the number of hosts we want to use for the data, and also the parameters for the variety that we want to exploit. So like specify a number of cores and number of threads. And then with this export array function, we can actually transfer data from the server side into a Python variable, which is accessible from the Jupyter notebook. Okay, with this I conclude this presentation. I just want to give a very brief recap of what has been shown in the first slide. We saw the different data management challenges, and now these have been addressed by the Ofidia framework, which provides a scalable architecture, support data distribution and partitioning, and provides a wide set of parallel operators. And finally, I introduced the Ofidia module, which hides the complexity of the high-performance computing infrastructure by providing a user-friendly interface. And we will see this in the next demo. Here I just provided some reference, as well as some further readings that might be interesting. And so, thank you everyone for for the attention for this presentation. If you're interested in Ofidia, you can find other info on the Ofidia website. You can also contact us. So please, if you have any questions, just write your name and question. We'll read them and address them in these few minutes before moving to the demo. Okay. In the meantime, maybe Fabrizio can start sharing his screen so we can move to the demo session. Okay, I see a question about the slides. Yes, we will upload them after the session on the same GitHub repository, so you will find all the slides there. We can move to the next part of this session, which concerns the demo about the Ofidia module. This will be presented by my colleague Fabrizio Antonio from CMCC. So Fabrizio, the stage is now yours, so please.
Thank you, Donatello. Hello everybody, my name is Fabrizio Antonio and I'm a Junior Research Associate at the Advanced Scientific Division of the Euro-Mediterranean Center on Climate Change. In this demo, I'd like to show you a notebook with some simple examples of analysis implemented with the Ofidia Python interface called Ofidia. I'm going to use the Jupyter environment recently deployed on the Zeus Performance Computing Cluster at the CMCC Supercomputing Center with the aim of supporting CMCC data scientists in their daily research activities. Anyway, you can find the same notebook with just minor differences also in the HPDA VIS training virtual machine image provided for this first session of the ESiWACE2 online training course on high-performance data analytics and visualization. We'll now have a quick look on what you find on the virtual machine. Here, we can see the virtual machine that has been set up for the training course. First of all, check the README file available on the desktop, which provides some instructions that must be executed every time the virtual machine is booted in order to start the needed services, such as the Ofidia server and the Ofidia IO server. Check also that you have the latest version of the training material. The repository for the materials for this first session is placed on the desktop under the HPDA VIS training folder. To get updates, just run the git pull command into this folder, and this will check if there is any update on the GitHub repository. Once the environment has been started, we can run the Jupyter Notebook application from the shell. A browser window will pop up with the interface of the Jupyter Notebook. The notebooks are located on the desktop under the HPDA VIS training session 1 folder. And in particular, the notebook related to the demo are placed under the demo folder and is called Ofidia Overview. Here there is the outline notebook, which provides a summary of all the notebooks available in the folder. As indicated in the preliminary info section, to run the demo notebook, as well all the example notebooks, you need the SNF5 data, which can be downloaded from the ESGF repository using the provided links. These two files we are going to download refer to the CASMAX and CASMIN variables and are part of the SNF5 dataset produced by the CMCC from the CHES model, a coupled system model developed for simulating past, present, and future climate states. The notebooks should also work fine with files related to the same variables and produced from different models by other institutes. As anticipated, I'm going to run the demo on the Zeus HPC cluster. With respect to the virtual machine, which is limited to the laptop or machine resources, Zeus provides access to a multi-node cluster for data analysis. The cluster consists of 348 dual processor nodes, 96 GB memory per node, about 13,000 processor core, 4 petabytes of storage, and a peak performance equal to 1 to 2 petaflops. This is the Jupyter interface of the CMCC data science environment. And in the session 1 demo folder, we can find the Ofidia overview notebook. You can try to follow the execution running the notebook in the virtual machine step by step. This notebook provides some basic examples of how to use the Ofidia framework features for climate data analysis, and in particular, it shows some of the main commands from the Ofidia module. As Donatello anticipated, Ofidia is an open source Python library developed by CMCC to interact with the Ofidia framework, and it represents the programmatic interface for the framework. In the first cell of the notebook, we are importing the Ofidia module. The library provides two main classes, the client class and the cube class. The client class implements the logic to manage the submission of commands and workflow and treat the end responses. It also takes care of managing the session. The cube class, on the other hand, provides a more user-friendly interface abstracting from the declarative format used to define the operator's commands in the client class. It provides an object-oriented approach defining the cube data type in Python, which refers to remote data cubes on the server side. In addition, it maps all the operators as methods of the cube class. The cube class defines two types of methods according to the type of the operator. Class methods concerning the operators which are not related to a particular cube object, for example, those for managing the file system, and the instance methods concerning operators applied directly on a cube object to access and manipulate it, and this typically results in the creation of a new cube object as output. We can run the set by pressing the Run button on the top of the Jupyter interface or by pressing Shift-Enter. Then we use the setClient class method to set up a connection with the Ofidia server based on the provided arguments, the hostname, port, username, and password. The connection arguments can also be automatically inferred from the environment if these have been exported, for example, through the bash.rc file. In this case, we can set readEnd to true, and the function will automatically retrieve this information. After running this cell, the text displayed below shows that the method was able to successfully contact the server with some other server information concerning the session. Once the connection has been set up, we can call all the instance and class methods of the cube model to submit the corresponding operator on the Ofidia server-side components. However, on the Zeus HPC cluster, we need one more step. That is the deployment of the I/O and analytics servers on the Zeus compute nodes. We can do that by running the cluster class method, which is a wrapper of the OPH cluster operator. As parameters, we set action to deploy to try to reserve hosts and start I/O servers. We choose the number of I/O servers to be started, the name of the user-defined partition to be used to group hosts, and we set the operator execution mode to async so that the execution continues in background. Once a command has been run, the related processes are submitted as LSF jobs on the cluster. We can check the resource allocation by using the bjobs command, which displays and filters information about LSF jobs. But we can also use the cluster method again by setting the action parameter to info to get information about the deployed cluster. When the jobs are in running status, the cluster has been deployed, and the output of the cluster method shows some information about the cluster and the reset partition. Of course, this step is not needed on the virtual machine, since there is only one node and will always use the default main host partition. In the following cells of the notebook, we are going to import an Sdf file from the training data folder. Here, I'm using a TASMAX file, which is part of the SNP file dataset produced by CMCC from the CMCC CM model, a coupled atmosphere-ocean general circulation model, which works at a higher resolution than the CHES1. But of course, since on the virtual machine we have limited resources, we were forced to use files with small size there. Here, on the Zeus cluster, as a result of our scalability test, we could have used a bigger file, but as we'll see very soon, importing such files sequentially will take too much time. So we can run the ncdump command to explore the structure of the Sdf file. As we can see, it contains a three-dimensional variable called TASMAX, which represents the daily maximum near surface air temperature. The variable is organized with respect to time, latitude, and longitude dimensions. The output also shows a list of global attributes used to describe the source of the data, the imposed experiment conditions, the contents of the file, licensing restriction, and other information useful for analyzing the data. We can also explore the structure of the Sdf file by using the explore and see method. Similarly to the previous case, the output shows the dimensions and their sizes, the variable list, the type and the dimensions on which each of them is defined, and some other information about metadata and global attributes. To create a new data cube from an Sdf file, we'll use the import and see through method, which corresponds to the OPH import and see through operator. Here, we are specifying through the impbeam argument that we want to import data so that the values on the array are organized according to the time dimension. This will improve the efficiency of the analysis that we are going to run. We need to specify the path where the file is located, the name of the measure related to the Sdf file, and the name of the IO host partition used to store data, which is the partition previously deployed with the cluster command. On the virtual machine, as said before, by default, the first available host partition will be used. As first example, we run the import command with a single thread. The method creates a new data cube on the Ofidia server-side components by loading data on the IO and analytics servers. At this stage, nothing is being read from the file on the notebook. The myCube object contains just a reference to the cube available on the server side. Just a few seconds and the import is finished. In this second example, we are using 18 parallel threads per process to speed up the import procedure. And as you can see, now the import took only 6 seconds. To inspect the cube structure and its dimension, as well as how it has been partitioned, we can run the info method on the myCube object. The output shows that the cube has been partitioned on 2 I/O analytics servers, each one managing 120 fragments. By default, the number of fragments is equal to the size of the outer dimension, excluding the time. So in this case, the total number of fragments is equal to the latitude size. The output also shows the data size and the number of elements forming the data cube. The dimension information table shows the cube dimensions jointly with their sizes. We can see that, as requested in the import and sync command, the time dimension is the one used as implicit array dimension. Now we can change the fragmentation level by setting the nfrag argument. Actually, you don't have this example on the virtual machine, since the file you are using is too small to take advantage of the benefits of fragmentation. In this case, we are setting the number of fragments per I/O server to 24 in order to have the same size for each fragment. The fragmentation is useful to improve the parallelization process, but of course, a too high fragmentation may introduce an overhead related to the fragments management. We can run the info method again. Sorry. On the cube. And we can see that now the cube has been partitioned on 2 I/O server and the server, each one managing 24 fragments, each one consisting of 2,400 rows. Now we can inspect the virtual file system with the list method. And this shows that we have 3 cubes in the user space created with the previous import commands. The PID provides a persistent unique identifier associated with these cubes. The description argument used in the import helps to relate data cubes to the operators in a more mnemonic way. If we want to get additional info about the methods and the arguments, we can use the Python help function. And here we see all the arguments and the possible values, for example, for the list method. Once the first cube has been created, we can run the Ofidia data analytics operator to process data. In this cell, we are performing a subset of the original cube on multiple dimensions by specifying the subsetting range for each one. In this case, we are using the actual dimensions values, but there is also the option to specify the dimension indexes by changing the subset type argument from core to index. The method will create a new data cube object without modifying the original one, still on the server-side component. So, my cube true will just hold the reference to this new cube. If we inspect this cube structure with the info method, we note that now each dimension size is smaller with respect to the original cube. The explorer method allows us to see the values stored in the data cube. And the limit filter argument tells the method to retrieve just the first line of the data cube. Here we can see the temperature values associated to the first latitude and longitude point. The method allows also specifying a subset filter as in the subset method in order to inspect only the values we are interested in. And this is very important to avoid unrequired data movement, since this function is designed only for data inspection and not for reading data blocks. Here we'll see how, so for example, here we are extracting only 2 values for lateral long and 4 values for the time dimension. Let's now perform a data reduction operation on the subset cube to compute, for example, the maximum of the whole time series. We can do that by using the reduce method, which is one of the most used for analysis together with the subset. The operation argument specifies that we want to compute the maximum over the array. This method supports a wide set of data reduction operations like minimum, average, standard deviation, and others. You can check the Ofidia operator documentation to get all the possible options available. The info method on this cube shows that the time dimension has been completely aggregated. We can now reorganize cube with the roll-up method to handle it more efficiently in the following step. This transforms the longitude dimension into an array-oriented dimension. The info method shows that myCube4 has now longitude as array-oriented dimension. Time dimension is just kept for back reference, but this dimension does not exist anymore. Now, if we run again the list method, we can see that at this point we have created several data cubes. The description argument using the previous methods help us to understand which operator each data cube refers to. Now we can use the result produced by the data reduction operation to get a map. The export array method allows moving the data from the server-side components into a Python-friendly structure on the notebook. This data can be easily used with other Python libraries such as CartoPy, Matplotlib, or NumPy. CartoPy is a Python package designed for geospatial data processing in order to produce maps and other geospatial data analysis. It includes a programmatic interface built on top of Matplotlib for the creation of publication quality maps. At this stage, the data size of myCube4 has been reduced with respect to the original importing file. And this is important since this is the first time in the tutorial that we are moving the full data from the server side to the notebook. As we can see in the picture, the return structure is basically a Python dictionary with 2 main keys, measure and dimension. The measure contains a single subdictionary filled with the variable values organized according to the dimension order, and the dimension keys contain multiple subdictionaries, one for each dimension. And for example, this is the output related to the dimension key. In this cell, we have a function implemented using CartoPy and Matplotlib for the plotting, as well as NumPy for minor adjustments to the data structure. In this function, we are using the measure and dimension keys to access the values of the exported data. We can see in the result of this cell that the map shows just a portion of the whole globe. We can also export data to an Sdf file by using the export and see-through method. We just need to provide the output path and the output name. And then we can check and explore the exported file with the explore and see. As we can see, we now have a 2-dimensional variable organized with respect to the latitude and longitude dimension. Now, what if we want to consider the whole spatial domain for our analysis instead of a subset? We can do that by applying a different subset on the original imported data cube, referenced by myCube object. Since every operation creates a new cube, the original one is still available in the cube space, and we don't need to import it again. And this is important because the import operation is one of the most time-consuming operations. In this case, we are subsetting only on the time dimension using a filter in a more human-readable form, specifying the range as a date. This can be done by setting the time filter argument to yes. The new data cube now have the full length of the lat and long dimensions, but just a portion of the time dimension, as we can see from the info output. We can run the same previous command in order to aggregate data on the time dimension and reorganize it. And then export this data and plot it on the map using the same function we used before. We can see that the map now shows the temperature over the whole spatial domain. Let's now consider a different scenario where we want to plot the minimum value for each point of the spatial domain. We can start from the previous new myCube object, the last subset one, and run the reduce method with operation set to min. By using the same methods and functions described before, we can get a new map which shows now the minimum temperature for this dataset. As another example, we can use the predicate evaluation operation to identify the days with temperature below a given threshold. In this case, we are going to use the apply method, which allows executing a query on a data cube, where the query is basically an Ofidia primitive or several nested primitives used to run array-based operations such as subsetting, data aggregation, array concatenation, and predicate evaluation. In particular, the OTH predicate primitive evaluates a predicate as follows. For each item of the input array, if expression 0 satisfies comparison, then expression 1 is executed. Else, expression 2 is executed. So, in this way, all values below the given threshold are set to 1. Now we can count days below the given threshold on yearly basis by running the reduce true method. Unlike the previous reduce method, which does not take into account the concept hierarchy and performs a reduction operation on a data cube with respect to implicit dimensions, the reduce true methods perform a reduction operation based on hierarchy and in particular according to the concept level argument. In this case, we have set this argument to y in order to aggregate the time array on yearly basis. As shown by the info method, the time dimension size is now 5, as the years which the input data refers to. We can now select the first year using the corresponding index, and finally plot the resulting map using Cartopy and matplotlib. And this is the map showing the number of days in 2096 with temperature below the given threshold. So far, we have seen how to run the most used Ofidia data analytics operators to process data and how to plot the retrieved output on a map. Now, what if we want to process time series and plot them on a graph? Starting from the imported cube, referenced by the myCube object, we can extract a single time series for a given spatial point. To do that, we use the subset method, specifying the actual dimension values and subset filter. For the time dimension, the option time filter is enabled so that we can use a user-friendly date format to select the desired year. For example, we can select the year 2096 by using the time interval bound separated by an underscore. We can now use one of the available primitives, for example, the Ofidia hash, which computes the moving average operation on each element of the measure array. As described before, we will use the apply method to execute the query on a data cube. In this example, we are computing a simple moving average on the previous 7 elements as indicated by the last 2 arguments of the primitive. Finally, we can export and plot the 2 time series on a graph. As another example, we can use the OTH sum scalar primitive to convert temperature from Kelvin to Celsius degrees. This primitive simply sums the given scalar value to each element of the measure array. We can apply this operation to the previously subsetted cube related to year 2096 and plot the resulting time series on a new graph. Now, let's perform a linear regression operation to extract the trend of the time series. In this case, we are going to apply the OPH GSL fit linear coefficient primitive to the measure array in order to compute the linear regression coefficients. The mass provided as the last argument of the primitive indicates the best fit linear regression coefficient to be extracted. This configuration will extract the intercept and the slope. And this is the scatter plot showing data with respect to the time dimension and the linear regression line. Another interesting use case could be computing the difference between 2 time series. Starting from the imported data cube, we can compute the average value over each time series. In this case, we are setting the concept level argument to m in order to aggregate the time array on monthly basis. Then, we can perform 2 subset operations similar to the last performed one. We can select a given spatial point and extract, for example, the first and the second here by using the corresponding time interval bounds as in the previous case. As you can see from the output of the info method run for one of the subsetted data cube, the time dimension size is now 12, while the latitude and longitude sizes are 1 since we have selected only one spatial point. To compute the difference between the 2 time series, we can use the intercube operator, which executes an operation, the difference in this case, between 2 data cubes with the same fragmentation structure and returns a new data cube as a result of the specified operation applied element by element. Then we can use matplotlib to make a bar plot showing the difference for the maximum near surface temperature between 2097 and 2096. Until now, we have run several operators, so the virtual file system contains multiple cubes, as shown in the output of the list method. Once we are done with analysis, we can clear the space and delete all the cubes with the delete container method. As we can see, the virtual file system is now empty. Before concluding, I'd like to show you some examples of massive operations. A massive operation refers to the possibility to apply the same operation over multiple files or data cubes by submitting only one command. Let's see what I mean with some simple examples. First of all, let's create a new container to organize all the data cubes we are going to produce. We just need to provide the container name, the names of the dimensions allowed, and their types and cost hierarchy names. In our TaskMax data folder, we have several early files from 1850 to 2005. For instance, we want to import files from 1980 and 1989. The client class supports the execution of massive operators. A single method, submit, is used to submit any type of commands to the server side. So we can use it to submit the import operator to the Ofidia server, all cubes in parallel from the input folder. As we can note, the inner command associated with an import operation follows the format of an import operation except for the parameter source path, which has to be set to a string of semicolon separated filters. Filters on the source path can be specified in square brackets in order to trim down the selection. In this example, we are importing all the files whose name matches with the provided pattern and contained in the path folder. In a similar way, we can perform a massive subsetting operation over each imported data cube. Here, I'd like to focus attention on two subset arguments. The subset filter, which now refers to a season, and this is another way to subset data over time by selecting a season using the corresponding code. And the cube argument, where level equals 0, means that we are considering as input cubes all the data cubes produced at step 0, the import and sequence. Now we can compute the average over time for each year. To do that, we need to specify the data cubes produced at step 1 as a list of input cubes. If we run the list method, we can see how running only 3 commands resulted in 30 data cubes in total, 10 as the imported years for each of the previously performed operators. We can also extract values and plot output data on map of the average years. In this case, we already have data cubes in the Ofidia framework, and we want to use them from the Python modules. We can use the cube class constructor to create a new cube object in Python and link it with the remote data cube based on its persistent identifier, which is the PID argument. So we just need to replace the PID argument in the constructor with one of the data cube PIDs related to a reduced cube shown in the bubble list. For example, we are considering the last one. And this is the map for the selected data cube. Once again, we clear the space and delete all the cubes with the delete container method. Just one last step to perform on the Zeus cluster. We have to undeploy the I/O and analytics server in order to free cluster resources. To do that, we can run the cluster method as we did at the beginning of the demo. We just need to change the action to undeploy in order to stop reservation and I/O server. And that's all for the demo. Thanks for your attention.
Okay, thank you, Fabrizio. Are there any questions about the demo? Again, please use the Google Doc to write your questions, and we'll address them. Besides, we can already start the last part of this training session, which concerns to the actual hands-on. So the goal now would be to try to apply what was presented during the demo on the smaller files that Fabrizio mentioned. So to design, you should use the VM that we prepared. I'll share anyway my screen concerning the VM, so we can so just show you. Actually, Fabrizio already showed that, but go into this on the desktop on the HPDA file, and then open session 1, and here you will find the outline. The outline shows the various notebooks which are available. And after you have downloaded the data, the goal of this last part of the session is to run these hands-on notebooks, starting from the first one, which is this basic notebook, and will be connected to during the whole hands-on session. So if you have any issues, both concerning the VM and also concerning the execution of this notebook, you can write us, and then maybe after we'll try to run together this notebook. So there are 3 notebooks here. Let's start with the basics one, and then see how many we can complete during this session. So anyway, all the material is available also later, so you can actually try to run this even after. We also provided some example notebooks if besides the hands-on you're interested in some actual examples of execution by Ofidia. Okay, so as said, please let us know if there are any issues during the execution of the notebooks. Starting from the big one, we'll be online and check on the also on the Google Doc regularly, and in like 10 minutes maybe we try to run this notebook together to see if there are any points which might be which might cause any issues, or might not, or there are some things which are not easy to understand. One thing to mention is that the notebooks are of increasing complexity. So the first one is basically a tutorial you can actually run and just follow, and then the following 2 will be a little bit closer to some sort of exercise in which you have to actually try to apply what was presented during the demo, and also in the previous notebook to complete them. And in any case, we also provided for every hands-on notebook the complete notebook into the example folder. So you will find the whole notebook. So if there are any issues in completing that, you can also have a look to the complete example to try to compare your implementation. Okay, so there is a question about thinking about ensembles of scenario simulation. The effort to load all the data into Ofidia for interaction might be enormous. Given the server people work on the same data, how can the computational effort be reduced? for example, should some standard output process data be stored for further use. We have implemented an example of ensemble analysis by using the Ofidia workflow engine, which will be covered in the next session concerning Ofidia. Basically, in that case, we were able to use this workflow engine to run multiple operators concurrently on different data sets. The test that we've done was around 18 models working on historical and RCP data. The import phase can, of course, take some time, but if we can run it with multiple operators, the experiment doesn't take a long time. Of course, it can be useful to start from some pre-processed data to reduce the import stage. And also another related issue is concerning the input data. For example, if we already have locally, like for example, being connected to an Sdf data pool, it would be, for example, easier to get access to a wider range of data. Or to this end, we are working at the Advanced Scientific Computing division to the analytic sub-concept, where we actually think of having a sort of a computing environment with the data for a set of variables for all the different models. So that can, of course, speed up the data preparation time, and then with Ofidia we can run multiple operators and read parts of this data as needed, using also the optimized data layout import feature. Okay, so I'm not sure how many of you were able to run or complete this. Doing this virtually is a little bit more complex to provide assistance or to check, but maybe it could be useful just to run the notebook very quickly. It basically follows many of the points addressed during Fabrizio's demo. So I'll very quickly go through this notebook. After starting up the service, you should be able to connect by running this shell. So once we're connected, we can then check our cube space. I already have some other cubes because I ran another notebook earlier, but you should have an empty list if this is the first one that you're running. Then with this import one, you can load the taskmax file. As Fabrizio mentioned, this is smaller than the one we tested on the Zeus cluster, because here we have limited resources in the VM, and we are loading this into the IO server running this command. In this case, you can also run it with not 4 cores, but it might take basically the same time, since again the VM is actually using virtual resources. As you can see in this case, it is even worse, and this can happen because of course on the VM, since we're using virtual cores, and the access to the file system might even not be that fast. It can actually take more time if you're using more cores than what's needed. Consider that this data set is 33 megabytes, so a single core is more than enough to run the whole processing. So at this point, we should have 2 new cubes. Here we can see that we got these max temperatures and min temperatures. We can check through the help inline Python command the full set of arguments of the cube class. This is a very long list with all the possible operators and the arguments available. And after that, we can run some analytics operation. For example, the reduce2, which basically aggregates the whole time series, providing a single value. And if you run this, we'll see that we have basically a simple grid with no time step, and this is very easy to map this into graphical output. We can also change the argument by using a different concept level, for example, by aggregating on year, or by using the maximum to compute the maximum values. The methods can also be appended, since in Python each method creates a new cube. We can actually append the methods. So if like we have task mean reduce, we create a cube, and then we can run the merge on this cube, appending the method, and again we can append the aggregate on this new cube, and then we'll just keep track of the last cube. Now we can run the intercube, as also for Fabrizio showed the case we're using the task max cube, and then passing as second cube the identifier of the task mean, and then compute the monthly mean to have the average, and we can see that these are the values we are computing with the difference of the maximum and the minimum value. And then we can export this data and then plot it on a map to show the diurnal time range, which is the difference between the maximum and minimum value. We're using a very similar function to the one shown during the demo. This uses matplotlib and graph2bind. We'll take a couple of seconds on the virtual machines, and at the end what we have is something like this, which basically the dots which are more dark are those where the difference among maximum and minimum temperature is bigger, whereas those which are close to light yellow are those where the difference is minimal. So we can empty this, and after that, if you're interested, you can also run the summer days notebook, which implements a different type of indicator. In this case, we will use the predicate primitive with the apply operator to detect all the points which are over a given threshold. And I'll leave this to you if you want to run it. This has to be completed according to the arguments, similarly to what was provided in the previous notebook. And then there is a third exercise, which is the linear regression, which is similar to what Fabrizio showed during the demo. In this case, you can use another primitive, which is the GSL fit linear coef to compute the coefficients to get the trend line. To compute the trend line, then you can plot this by using the matplotlib features, and this will allow to create a scatter plot and then a regression line based from the regression function. If you're interested in the notebook, as said previously, you can have a look also at this example notebook. So just now, to conclude this session, go back to the presentation. So I just wanted to remind you that the next session is next Tuesday, and will concern more the visualization aspects, and will be given by our colleagues at DKRZ. We'll upload the slides on the GitHub later today, and so if there are no questions, I will thank you all for attending this session, and see you next week.